Hi, everyone. My name is Celeste Hollenbeck. I'm a PhD student at the University of Edinburgh, and this is our study that we recently did. It's called Investigating Magic Numbers, Improving the Inlining Heuristic in the Glasgow Haskell Compiler. So this work is part of a larger body of work. And we basically want to improve inlining in GHC. And we have some more specific ideas of how we want to do that we're working on. But we want to do it with a data-driven approach. So this particular study is kind of the origin of some of that data. So first of all, what is inlining? I don't want to assume that all of you know, because I don't think that this problem should be reserved for the people who already know everything about it, because there are very few of them, and I'm not even one of them. So let's take a really classic example. It's compile time. We're in GHC. We have a function. This function is named f, and this function takes in a variable x, and it returns x times 3. And so let's say that we also have an expression that makes a call to f, and it passes in as x, a plus b. So it passes in a plus b and then subtracts c. So if we want to inline this function f in the expression with x is a plus b, then we simply rewrite f, substituting x with what's passed in, and we get a plus b times 3 minus c. So conceptually, it's very easy to understand what inlining is. But in practice, when we want to know when to apply it, that gets much more difficult. If we do it just right, then we avoid that additional jump to the function, and then we also get faster code. And part of that is because when we actually write the hidden thing inside the code, directly inside of it, we expose further opportunities for optimization. If we do too much inlining, though, bad things start to happen. Like we start getting bloated code, and then we also start seeing increased pressure on the instruction cache, and then registers start spilling, etc. So to make this cost-benefit analysis, GHC's inliner is a relatively complicated system. And if this graph here irritates you, that's good, because I made the font deliberately small and hostile, because the inliner is doing a whole lot of stuff that I can't fit to in one slide and explain in one slide. But on a high level, what the inliner is doing is it's looking at the thing that it's considering for inlining, and then it's calculating roughly the size of that thing. But then it's also calculating some sort of a discount that it might want to apply to that thing to offset the size. And then ultimately it's going to take the size, subtract the discount, and then if it falls beneath some threshold, then it's going to say, yes, I'm going to inline it. And all of this decision is based upon a whole lot of little smaller calculations, which we call heuristics. A heuristic is basically a best guess judgment, and they are all written by hand by a human being. And this is how it is in most compilers. So how do we know that GHC inlines poorly? We don't. So that's why we set out to find some evidence to confirm whether or not this is probably the case. In the search for this evidence, we were looking at code, and we made this observation that a lot of times people include this thing called an inline pragma. And an inline pragma is basically an annotation that you can put around the declaration of the thing that you would like inlined. And so GHC will come, and it will see this inline pragma, and it will try really hard to inline the thing. And sometimes this could be made for a performance gain. Sometimes maybe it's not, because an inline pragma can also be inserted in order to expose rewrite rules. But let's assume that oftentimes this is made because a developer wants to make something be inline, perhaps for performance reasons. And if that's the case, then we thought, okay, does this mean that maybe the developer has identified some sort of like a blind spot that GHC is not seeing, and it says, inline this thing because I know something that you don't. And perhaps this is like some sort of an indication of dissatisfaction. So to check this out, we downloaded all of Stackage. And then we filtered all of Stackage for packages that had inline Pragmas. And it turns out that in the snapshot that we chose, about 19% of the packages had these inline Pragmas. And that seemed a little bit high. So what do we do next? Let's try running their tests. Okay, so there was some bad news. About 39% of the packages that were in this snapshot of Stackage were using something called QuickCheck. And QuickCheck is a framework which produces new, fresh, random tests for every run of your test suite. So when we ran the tests, we saw basically a whole bunch of noise. But the good news is that 39% of these packages use something called QuickCheck, which means that they all used QuickCheck. So we basically took QuickCheck, and then we hacked the random seed to just be one number every single time it ran. So then all of those non-deterministic tests became deterministic, and our noise went away. So the question, now, did Pragmas speed up the tests? Sometimes. For the most part, they didn't have much of an effect. In a few cases, they slowed things down. In a few more cases, they sped things up. So in order to make this more manageable, because we didn't actually want to just kind of study the question of Pragmas, what's the effect of Pragmas, we decided to sub-select packages and look at a smaller set. And then we said, okay, let's look at packages that do have inline Pragmas, they do have tests that run, and then those tests run for more than 4 seconds, okay? These are the packages that we ended up selecting. The descriptions, they're in the paper. There's some more information about them. What's kind of more important to understand here is that we more or less ended up with, kind of a random sample of packages, 10 of them. Now, if we look at the effect of Pragmas for these particular 10 packages, about 6 of them sped up a bit. 1 of them sped up a lot. This one is called Poly. I believe it's a library for dealing with operations with polynomials. And its speed increased by about 154%. There were 2 other packages that slowed down a bit. And there were 1 or 2 that were about the same. We don't know exactly why the Pragmas did or did not work. We didn't investigate that far. Maybe they weren't meant to be put in there for performance reasons. Maybe they worked at the time and now they just don't work anymore. So we went a little bit further with this smaller set of packages as we intended to do. Right here, we're looking at some code in the inliner that computes the discount. I'll explain a little bit of what it does. But notice that there are some circles in here, and the circles are around magic numbers. They're just numbers that were hand-coded into this discount, and they stand out because they seem a little bit arbitrary. But this top one, we'll just go ahead and read the comment. It says a discount of 10 because the result replaces the call, so we count 10 for the function itself. So every time we see a function, we'll automatically give it 10 discount unit points because of what the comment is saying. And then we have another 10, so we subtract 10 times the number of arguments that the function is receiving, and it says discount of 10 for each arg supplied because the result replaces the call. And then further down, we have a few more magic numbers, like it's going over each of the arguments and deciding how interesting they are. If it's trivial, it calls it a trivarg, and it gives it an additional discount of 0. And if it's non-trivial, and this is all calculated and determined elsewhere, then it gives the argument a discount of 10, and then does some further things with the continuation. And it ultimately doesn't matter exactly what it's doing. But what we did is we looked at these numbers, and we thought, if we just randomize these? So we selected 10 magic numbers. 8 of those pertained to the calculation of the discount. 2 of those pertained to the calculation of the size. And then there are 2 on the bottom here, which were just included with GHC. One of them says the eagerness to inline functions in general, and another one is eagerness to inline dictionaries. And we just said, that tooling is already done for us, let's just throw it in. The rest of them, we turned these magic numbers into parameters that we could just pass to GHC, so at compile time it could stick those new random numbers in. And this is what we got over the benchmarks, which I will explain. So the black bars, that is what we saw before, with versus without Pragmas. The baseline here is default GHC, and we decided to take Pragmas out for the baseline. Let's pretend the Pragmas don't exist. The gold bars in the middle for each project, for each package, is the random search with magic numbers. We took the fastest configuration of magic numbers without Pragmas and used that number for that package. The blue bars, we left the Pragmas in. And then we did the random search with magic numbers. And then we took the fastest one, and that is each blue bar. It is noteworthy that with every single package, with some configuration of magic numbers, we managed to find something that was faster than default GHC. Many of them were significantly faster. Like we have 10%, 13%, 30%, 20%. Now, poly, this is a little bit misleading because that blue bar should be going way higher up because that's sped up by 338%. That's with Pragmas and with random search. It's also noteworthy if we look at poly and we take the Pragmas out and then we randomize things, we only get 14% improvement, which is much less than no randomization with Pragmas, which is 154%. Okay. So we did some additional calculations, and I'll go over the salient points. If we look at that previous slide, and we take the highest bar for each package, and then we compute the geometric mean speedup of the whole set, we see a possible speedup of 27%. That's like if we had some magical oracle that said, okay, if you do everything right with the inlining so far that you've seen, this is what you can expect to see. But the problem with that is that this is a single individual configuration of magic numbers for every single package, which means that we have 10 different configurations. So, all right, what if we look for the single best configuration of numbers across all of the packages together? With Pragmas, our speedup can be expected to be 22%. Not too bad. Unfortunately, we can't suck those Pragmas back up into GHC and take everything that we've learned from those Pragmas and then apply it to new packages. That knowledge is stuck in those packages. So, what if we take all the Pragmas out? We'll find the best single random configuration of numbers across all the packages. We saw 7% speed up. Not bad, but that's really a far cry from this 27% speed up over here that we have seen as possible. Okay, so here's some good news. If you take any given package, take the Pragmas out, and you randomize the numbers somehow, you have a 50-50 chance of doing a better job of execution time than default GHC. Half the time, it was faster. Cool, I mean, that's cool, right? Kind of. This graph just says we probably didn't search long enough. We only did 320 random configurations. I think if we'd gone a little bit longer, we probably could have bumped those lines up a little bit higher. Maybe we could have found a slightly better single configuration, but the deadlines were approaching and we needed the machine. And also, it doesn't seem like the magic number search is the correct solution to this problem. And this graph is kind of explaining why that is. So on this x-axis here, we have the parameterized arguments, and then these yellow diamonds are GHC's default numbers for each of those. And these lighter colored boxes represent the random distribution that we pulled from. And then each of these black dots for each argument is each package's preferred magic number for its best configuration. And I'm hoping it's pretty clear that those preferred numbers are scattered throughout the entire distribution for all of these flags. There's maybe a couple, like this fun folding fun, which was the general eagerness to inline a function, should probably be a little bit higher than default. But in general, all over the place. This is just another graph that illustrates pretty much the same point. We used more data points. We looked at all of the packages and we grabbed their top 3 configurations, but also such that those 3 were within 1% of their optimal speed up. And then we turned the parameter numbers into histograms and we just plotted them. It's still pretty much all over the place. There are a couple of parameters which seem to kind of form some sort of like maybe a normal distribution, really not many. Like maybe actarg over there prefers a slightly higher number, or the function itself, like the eagerness to inline the function, should be a little bit higher. For the most part, all over the place. Okay, so we thought, here's a really super naive solution. Like, what if we select some really small number of different configurations of numbers, and then we'll assign packages to one of these small numbers of these small numbers of configurations. And that's what we did here. We were super, super stupid, and we were just like, let's run it against each of the configurations and assign it to one of those. And if we do that, with Pragmas, then we see about 26% speed up. If we do it without, I remember, I think it was like 10% or something. It wasn't bad, or 9%. Don't quote me on that, even though it's my paper. So anyway, again, this is not a great solution, because coming up with some sort of a sophisticated clustering algorithm that is going to reliably work is kind of a hard problem in itself. And if we're going to devote that much time and energy to a solution, I actually think it should be that we should just completely rethink the inliner. And I have some super cool ideas of how to do this that I'm working on, and they involve machine learning, and they're super cool. If you don't like that approach, though, perhaps you can present something wonderful of your own. So that's what I've got. It's probably got some flaws in it, but I think that it's encouraging enough that keep going. I'm going to keep going. Ah.